This video is about waves and optics. In physics, many phenomena can be described using wave physics. And the general equation for waves is this equation here, where a wave's speed is equal to a frequency of a wave multiplied by a wavelength. We use the Greek letter lambda for wavelength. Any phenomenon that has some sort of oscillating nature can be described as a wave. For example, a pendulum swinging backwards and forwards, or a spring bouncing up and down. Sound can also be described using wave physics, as can light and other mechanical waves like water waves and waves in springs. If we draw a graph of the displacement of something, for example, the physical displacement of the surface of the water versus distance, we get a graph with a curve that looks like this. And the distance from one peak to the next peak is equal to the wavelength. Indeed, the distance from the trough to the next trough is also a wavelength. However, we could, on the x-axis, instead have time. And this would be an example where we're watching a single position and watching something oscillate up and down, and plotting a graph of its displacement versus time. In that situation, the peak to peak on the x-axis is not a distance because it's time on the x-axis. The peak to peak is what we call the period or time period of the wave. A wave travels a distance equal to one wavelength in a time equal to one time period. And if the period is measured in seconds, then the reciprocal of the period, that's 1 divided by the period, that will be equal to the frequency in hertz. Now these two equations will get you started with most of the waves problems that you'll find. But do be careful to make sure your units are as they are written here. Wavelength in meters, frequency in hertz, wave speed in meters per second, and period in seconds. And of course you'll have to rearrange these equations as well. Occasionally, just to try to trip you up, a question will appear that talks about distance, time and speed. And you'll have a look at these two equations and decide you can't answer it. So don't forget that speed, as a general equation, is the distance that you travel divided by the time you take. And remember that we use s for distance or displacement in physics. It's easy to forget about this equation when you're dealing with the others. So for the next part I'm going to be using water waves, but actually the same physics applies to all sorts of waves. Here I've got a picture showing a two-dimensional water wave, and you can see I've drawn red lines along the peaks of the waves. Those red lines are called the wave fronts. If I were to place a ball in this wavy water, the ball would go up and down. Actually, it would go in a bit of a circle, but it would go up and down as the waves pass it. The wave itself would be moving in a direction perpendicular to those wave fronts. So in the next diagram, I'm going to view this wave from above. When waves pass through an aperture or gap, they can spread out. The technical name for this is diffraction. It might look something like this. Rather than the waves passing straight through the aperture as a straight beam, there's some spreading either side. And the angle of diffraction or diffraction angle will tell you how much spreading there has been. The bigger diffraction angle, the more spreading there has been. The wavelength of the waves is the distance between two adjacent peaks or wavefronts. And if we say the aperture size is d, as I've indicated on this diagram, then the angle of diffraction is related to the ratio lambda over d. That is to say, if lambda over d is larger, we have a larger angle of diffraction. And if lambda over d is smaller, we have a smaller angle of diffraction. For the rest of this section, we'll be using ray diagrams, where a ray is always 90 degrees to a wavefront and indicates the direction that wave energy is being transmitted. We're going to be looking at optics. And a good place to start with ray diagrams is with mirrors. The reflective side of this mirror is on the left. This is a plane mirror because it's a straight line, and so it will produce specular reflections. What that means is that if all the rays were coming in parallel, then the rays would also leave the mirror parallel. But we are going to consider the rays coming from this object I've labelled on the diagram here, and where the object appears to be to an observer in different positions. So this eye indicates where the observer is, and let's draw a ray diagram indicating reflection. This ray is called the incident ray, and this ray is called the reflected ray. The angle of incidence is the angle the incident ray makes to the normal, where the normal is this imaginary line that is 90 degrees to the surface of the mirror. The reflected angle, or the angle of reflection, is the angle that the reflected ray makes to the normal. And with specular reflections, in fact with all reflections, the angle of incidence will always equal the angle of reflection. The eye doesn't know that there is a mirror here, so the eye observes the light coming from somewhere along this dotted line. If we want to work out where along this dotted line the light appears to be coming from, we need a second point of view, a second eye. So if I were to place my second eye in this second position down here, where would the object appear to be? Here I've done the same thing as last time, where I've drawn an incident ray and a reflected ray, such that the reflected ray has the same angle of reflection as the angle of incidence. And just as before, for the blue ray, it looks as though the light has originated from somewhere along this dotted line. And the only position where those two lines are in agreement is here. So this will be the position of our image. The image is the point from which it appears as though the light rays are diverging. A line that connects the object to the image will pass through the mirror at 90 degrees. And the distance from the object to the mirror is the same as the distance from the mirror to the image. This is the sort of ray diagram for reflection that you may have to reproduce. And remember that the angle of incidence must be equal to the angle of reflection, so take care when drawing this diagram to make sure these angles are the same. The last two types of ray diagrams you'll have to master are the lenses. And the two types of lenses you'll look at are convex lenses and concave lenses. But we don't draw the lenses like this, because that would be far too difficult. We have a simpler symbol that we use instead. For convex lenses, we use the symbol that I've shown on the left, and for concave lenses, we use the symbol that I've drawn on the right. Let's start by looking at ray diagrams for convex lenses. So here is our lens, and an imaginary line that passes through the centre of the lens is called the principal axis. The lens has a point called a focal point. Rays that are parallel to the principal axis when they enter the lens pass through the focal point after the rays leave the lens. And the distance from the centre of the lens to the focal point is called the focal length. There's a second focal point on the near side of the lens. So let us consider placing an object on the near side of the lens and seeing if we can work out where the image of this object appears to be. Here is our object, and we are just going to look at rays emerging from the top of this object for now. There are three principal rays that you have to learn. The first principal ray passes parallel to the principal axis and then refracts through the far focal point, like this. The second principal ray passes through the centre of the lens undeflected, like this. Now already from this diagram we can identify the location of the image. But for completeness I will show you the third principal ray. The third principal ray passes through the near focal point and then refracts parallel to the principal axis, like this. And you can see all three rays appear to cross at this point here. And so if I were looking at this from the right hand side over here, it would appear as though the rays have come from that point where the rays all cross. That is our image. Remember, an image is the point from which it appears as though the rays are diverging. And it appears as though the rays are diverging from this point here. Now, because the light rays do actually cross through this point here, this is called a real image. Now, of course, we've only located the top of the image from the top of the object. What if we were to repeat this from a point halfway down the object? Well, by repeating the same three principal rays, the first principal ray parallel to the principal axis and then through the far focal point, the second principal ray straight through the centre of the lens undeflected, and the third principal ray through the near focal point and then refracting parallel to the principal axis, we can see that all three rays converge at this point here, and therefore all three rays appear to diverge from that point to the right of this diagram. And so we have an image of halfway down the object that appears halfway down the image. And if we were to repeat this for an infinite number of positions all the way down the object on the left, then we would produce a series of images all the way down the image on the right. So for that reason, we only tend to bother drawing the image from the top of the object. So what if we were to draw our object here, closer to the lens than one focal length? We follow exactly the same three rules. The first principal ray was parallel to the principal axis and then refracting through the far focal point. The second principal ray passed straight through the centre of the lens undeflected. Now at this point you probably quite correctly notice that the rays do not appear to be converging. At least they don't converge anywhere to the right of the lens. That's because they are diverging from an imaginary point to the left of the lens, where the light doesn't actually originate from. This tells us that we are expecting a virtual image. Let's draw the third principal ray. Well, the third principal ray passed through the focal point, the near focal point. Oh dear, the near focal point is to the left of the object, so if I were to draw a ray coming down here, it wouldn't actually be incident on the lens. But what we really mean is that a ray that passes through the near focal point and through the object will then refract parallel to the principal axis, and we can use that rule. Okay, so the light doesn't actually pass through the focal point, but we can trace the ray through it, and so there's nothing wrong with that. Now all three rays appear to diverge from some point over here. Well, let's identify where that is. I've used dotted lines to indicate that the light does not actually pass through this point here. We are just projecting back the rays that we can observe. So the light appears to diverge from this point here. That is the image. And it is a virtual image because the light does not actually pass through this point. You could see that we could in fact construct the position of the image by using just the first two principal rays. The third principal ray is included here for completeness, but you really don't need to worry about it if it's going to cause you confusion. We can follow a similar approach for concave lenses. Let's draw our object. I've labelled my object with an O. Now the first principal ray passes parallel to the principal axis, just as it did last time. But now, because it's a concave lens, rather than passing towards the far focal point, the ray passes away from the near focal point, like this. And it can be difficult to see how that makes sense until you draw a construction line on your diagram. So by drawing this construction line, you can see that the ray here does indeed travel directly away from the near focal point. So the rules are almost the same, but in reverse. The second principal ray passes straight through the centre of the lens undeflected, just as it did last time. And as the case before, where we had a convex lens with the object closer to the lens than the focal length, here we have rays that are diverging rather than converging. However, we can already see that they appear to be diverging from this point here. The third principal ray is a really tricky ray, but it's going to help us identify the position of the image. The third principal ray passes towards the far focal point, but when it is incident on the lens, the ray travels parallel to the principal axis. So with the previous one, with convex lenses, the third principal ray was through the near focal point, then parallel to the principal axis. Now it's towards the far focal point and then parallel to the principal axis. So the rules are very similar, but everything seems to be in reverse and a little bit more tricky to draw. All three principal rays appear to diverge from this point here. So that point there is the virtual image. It's virtual because the light from the first principal ray and the light from the second principal ray do not actually pass through that point, it just appears as though that's the point from where the rays are diverging. So that is our virtual image. Now these are very tricky to draw, these diagrams, but if you can memorize the rules for the principal rays, then you'll be able to locate the image for any of these situations that you may be given.